Hi everyone, so welcome to our final meeting for the semester. Today we're going to talk about a pretty cool topic called the generative adversarial network. And this might sound very difficult to learn or anything, but the techniques and the idea behind this is really cool, really applicable, and it's nothing that we haven't really seen before. And so let's look at, okay, why do we care? Why do we even want a different technique? And the name implies generative, or has the word generative in it. That implies it's generating something. And it's been found that generative adversarial networks, I'll just call them GANs from now on, GANs, they are good at generating. If you guys are familiar with deepfakes, or that's the primary application right now. But let's look at this image right here. The input of the image is some hand-drawn bag or fashion bag or shoe that you're seeing. And the output of that, what the GAN generates, is a realistic looking shoe or realistic looking bag from our initial bad drawing. So this is cool, right? Okay, but let's look at the other image. It's a picture of people, faces, right? But none of these people actually exist. These are all generated faces, generated people essentially. And these people don't actually exist. They were generated by the GAN. So we'll learn about how this technique works, which is pretty cool. It's a relatively new technique. It was proposed in 2014, only 6 years ago. But it's seen a lot of growth and popularity in more research, and it's just a cool technique all around. So there's two concepts in the GAN. There's a generator and a discriminator. Okay, that might sound a little confusing too. Let's break it down. We actually have two neural networks in this case. Okay, so this is different from what we did before, right? Before we had only one neural network. The neural network, we would input some input, give us some output, and that was only it was only one neural network essentially. We have two in this case, and we'll see the uses of that. We'll see why we need it, and we'll see it's a pretty cool application of neural networks. And so, what are these networks doing? They're competing. Okay, the networks are competing against each other. It's an adversarial, right? Generative adversarial networks. They're adversaries to each other. They're in competition. And we'll see how they do it. But let's split apart the generator and the discriminator. What are they? Okay. The generator is one of the neural networks. And this generates new data. It does this from noise, but its goal is to trick the discriminator. The discriminator is the other neural network, it's the second neural network. The discriminator, so the generator is trying to generate new data, sort of self-explanatory. Generator generates new data. Discriminator, on the other hand, is the second neural network, and it's a classifier. And it tries to classify if the data is real or fake. Okay, it's a classification task for the discriminator, for our discriminator neural network. The generator, we'll see, we've talked about it. It's very similar to the YOLO, what we talked about in the previous lecture, the YOLO algorithm, where the YOLO outputs not a classification, but a whole nother image with boundaries, with a classification. So the generator, we'll see, is going to output a whole number output, whereas the discriminator is going to output a classification. Is it real or is it fake? And we'll see, there's a really nice diagram here. This is a really good image of what is going on. And we'll break this down. There's kind of a lot going on, but we'll see what's going on. Let's start at the generator, right? This is one of our neural networks. and it's going to be fed as input latent random variable noise. What exactly is this noise? This noise is image noise, right? You can see it's sort of in the shape of an image, right? A 2x2 matrix, a 2x2 array, or sorry, a 2D array. Uh, yeah, a 2D array. And so, but it doesn't look like an image. It doesn't look like anything, right? It's just random noise. This random noise is initially random, implied, right? So the image is going to have some random 0.1, let's say, or 0.5. How are those random pixels generated? They're generated by a normal distribution, right? So if we take the mean of all our pixels in this random picture, we'll get a mean of 0 and the standard deviation of 1, essentially. Not too important if you don't get that, but essentially it's random. The input, it just takes a random input. The generator, next, this is a little bit different, but similar to the YOLO algorithm. The generator takes this random noise and transforms it into an image. So this is what's different from our regular classification tasks, right? The output is not some 1D array. The output is a 2D array. And that 2D array corresponds to some image. But we can see here, okay, let's say we take some pixel. Let's say this is pixel 20. We take that pixel and it gets transformed to whatever that pixel is, to a different value. Because remember, pixels are just numbers. They're 0.1 if we scale the pixel, right? It goes from 0 to 255. But if we divide this by 255, we get some number from 0 to 1. And so we get, it's just a pixel from 0 to 1. So 0.1, let's say. And it starts off randomly, right? But then it's transformed into a pixel. And it means something, right? We can see here, we see a pretty good representation of a cat. And this is what the generator generated. But again, instead of it being a classification task, the output of this neural network, of the generator's neural network, is a 2D array instead of our regular 1D array. And we'll see how to do that. We're not going to have a lab because the semester's ending, but I'll show some code that represents this and shows how to do this. Let's look at the second part of it, real world images. This is our second part of the data. Real world images, actual data, not fake data, not generated data that are just generated by this network, but real images, real data. Both of these now, the image generated by this generator and this real image are next fed into this discriminator. Remember, the job of the discriminator is to discriminate. It's to classify. Is this image real or is this image fake? And the way it's doing this is it's getting two different inputs, two different image inputs in this case. It's getting an image of a cat, of the real cat, and an image of a fake cat. And it's classifying this. This is a classification task. Is it real or is it fake? This is a binary classification task. We've done this before with more labels, but this is just a classification with two different labels. And finally, we get the model's loss. And this is the loss, this is the cost function that our model uses to classify, is it doing a good job or is it not doing a good job? You can kind of see here, this image is a good job. The model's loss, which is what we get as an output, what we care about, is based on the discriminator. But the discriminator is based on the generator and the real image, the real data, the real images. And so we get a loss corresponding to what the generator did and what the discriminator did. And so they're competing against each other. The output is this model's loss, but it's a competition. the generator is trying to trick the discriminator. The discriminator is classifying, is this image real or fake? The generator is trying to trick the discriminator to take this fake image and treat it as real. The way it's doing that is by trying to generate better and better images. And you'll see where this is going, right? We're not only training a good discriminator, a good classifier, we're also training a good generator, where the input is some random noise, but the output is some really nice image, a really high quality image of whatever we want to get an image of. So let's look at how exactly they're competing. All right, this might look a little confusing, it might look a little intimidating, but let's break it down. We have min, max. That's very important, but we'll get into that. We see our cost function is a little bit different. We have first our discriminator, ignore the logs, they're not too important, but we have, let's look at the discriminator's output of real data. This is what our discriminator is outputting, the loss of our discriminator. It's the loss. If our image was real, then the loss should be a 0, right? Because for this particular area, the loss should be 0 because it's predicting that the image is real. Or yeah, it's predicting the image is real, and the image was actually real. And so we get a loss of 0 because real minus real is 0. If it's real, but it's predicting fake, it's a loss of 1. Just like a regular classification test. And this is iteratively improved as the number of epochs, as it starts off randomly, right? It starts off predicting things as real, fake, randomly. But it gets better and better as it understands what's real and what's fake. Because we know what's real, right? We feed this into it. The generator is what's providing the fake data. We know what's real and we know what's fake. Now we have this addition. What is adding to? It's adding to something. It's adding to 1 minus the discriminator as a function of our generator. What does this mean? The discriminator takes as input, the input to that discriminator, to that neural network, is the generator, right? In this case, the input to this discriminator was a real cat image, let's just say, a real image. But this time, the discriminator gets input the generated, the fake data. And this is the corresponding loss to that. And so if our discriminator predicts that this is a real image, it's going to predict that 1, right? It's a real image. But if we 1 minus this, right? We have this 1 minus here. We get a 0. We get a loss of 0. And so this is what we want because this is not a real image. Or sorry, if it predicts a real image of being 0. And so we get a loss of 1. And so because this is not a real image, but it's predicting it to be a real image, we get a higher loss. We get a loss of 1. Whereas if it predicts it as a 0, then we get a loss of 0, which is a lower loss, which is what it's trying to do. The generator, on the other hand, this is where the min and max come in. Let's look at this max of the discriminator. Okay. Actually the max of, so this is sort of corresponding to the generator actually, but this max generator, what it's saying is it's the generator is trying to maximize the loss of the discriminator. Essentially, the generator is reliant on this area right here, right? It's what it can affect. The generator is trying to make this loss higher and higher, closer to 1, right? Because our loss is from 0 to 1. And so The generator wants to maximize this loss. It wants to trick the discriminator. And the way it's tricking the discriminator is by generating better and better images. The discriminator, on the other hand, is trying to minimize this loss, just like a regular classification task. It's trying to minimize this. It's trying to get this loss to a very low level. And as such, it's basically doing a good job of whatever the generator is getting, it's doing a good job of showing this is fake, or this is real, this is fake, this is real. And so this is the main thing, this minimax operation. This is how they're competing. The competition is trying to minimize and trying to maximize, and they're competing. One, let's say the loss is getting, the discriminator gets better and the loss decreases. Now it's the generator's turn to generate better and better data. Now let's say the generator is doing really good and the discriminator is doing poorly. Well, now it's the discriminator's turn to do better and better and to decrease that loss. And there's this nice theorem. If you're not too interested, don't worry about it. But the theorem is really nice. But that basically, as we train, the optimal loss that we get for the discriminator and the generator is going to be 1/2 for both. Why is that? Because that means that the discriminator is doing really good, but the generator is also doing really good, which essentially means that the generator is outputting really good images. And so the discriminator is not sure if the image is real or fake. That the fake image is so indistinguishable from real. It's very hard to know for the discriminator to know if it's real or fake. And so it's just outputting a probability of 50%. It's not sure. It doesn't know if it's real or fake. And so it's 50% sure. Essentially, it doesn't know. It's just randomly guessing, right? Because we have, is it real, is it fake? It's just guessing. It doesn't know. It's 50% confident. Well, this is cool because this is the optimal scenario, essentially, getting a loss of 1/2, where our discriminator is really good. Our generator is really good. Our discriminator is also good, right? Just because it doesn't know, doesn't mean it's a bad discriminator. It just means the generator is so good, it's generating such real images that those real images, those fake images are indistinguishable from real images. Because we're not gonna have a lab for this semester, I wanted to provide some code. And this is from a really good TensorFlow tutorial. The link is right there, but this is for a particular task. And there's really nothing new to what we haven't learned. So essentially, but it is important to look at the shape of it, the specific neurons that are going into this, because those are important. Whereas in the regular neural network case, it wasn't that important. It is kind of important now. And this tutorial does a really good job of showing what is the expected output supposed to be. Let's break this down. So again, sequential model. The first layer is a dense layer of 7 by 7 by 256. It's getting an input shape of 100. So that's just a 1D array of random noise, essentially. This is, again, not too important, but it is basically for that specific task. And if you look at the actual tutorial, they're doing this for some specific task. And so this corresponds to what they want to show, essentially. This is just it's done a little bit differently than how we've done it, but this is just the activation. And then it's reshaping this to 7 by 7 by 256. This is, you can kind of see it, right? 7 by 7 by 256. So this is becoming a 3D array. 3D array is sort of an image, right? And this means something, right? 7 by 7, that's the image size of 7 pixels by 7 pixels. 256 is the color scope. right? We have 0 to 255 colors. And so we're gonna have a 2D image, but three-dimensional, because we have also colors at that. We have from 0 to 255, 256 colors essentially. All right. This assert modular output. This is nice to show you what the expected output is supposed to be. And so we see the expected output is a 7 by 7 by 256, a 3D array. Now let's look at the next layer. It's a conv 2D transpose. We haven't really talked about, but there isn't much difference from a regular convolution layer to a conv 2D transpose. All this is doing is, this is important if you want the output to be an image. Because in the previous task, we wanted the output to be some 1D array. In this case, we want the output to be a 1D image, an image of 2D or 3D shape. So we do the conv 2D transpose. Again, of 128 neurons, this is a little bit arbitrary. Again, this is our window size, our strides, just like our regular convolution layer. And again, the output of this model is a 7 by 7 by 128. So we're downsampling. We have the 256 colors, but we're downsampling that to 128 colors. They're not really colors right now, but they're just the number of neurons, or what the expected output is supposed to be. And again, batch normalization, it's just normalizing the output. So the output is going to be some number from 0 to 128, the pixel values. This is just normalizing that, either from the mean. So it could be the x minus the mean divided by the standard deviation. Probably, I'm guessing that's how it's normalizing it. And same with the activation, just like we've done before. They have another convolutional layer, transpose, of size 64. And then with 64 neurons of 5 by 5 and strides 2. The output is a little different, 14 by 14. The reason for that is because of our strides. We're sort of skipping throughout, and we have initially our image is 7 by 7. But now we're expanding that image to be 14 by 14. We're sort of doubling the size of that image. And same with normalization, same with the activation. Finally, we have our last convolutional layer. With an output of 1, we'll see why. Same with our size, same with our strides. But the output shape is 28 by 28 by 1. This is a standard image size, what a standard image looks like. The 7 by 7 image is a pretty small image. 28 by 28 is also small, but it's definitely seeable. And so that's why we have this 1 here, right? You can sort of tell the number of neurons corresponds to the output size. And the output is just, remember, 28 by 20. This is a 2D array, right? We sort of ignore this 1 here whenever we have a 1. But because we normalize, we could do this 1. And so we're getting rid of all color data. And so colors are represented by, now going to be represented from 0 to 1. Because we have this 1 here, because we normalize. And so the final output is an image of size 28 by 28. And this is exactly what we want. This is our generator model, which generates data, generates images. And so our size should correspond to what an image size is, 28 by 28 image. Our discriminator is a lot easier. It's something we've seen before. Just a classifier. We have our sequential model. We have our convolutional layer, a regular convolution, not a transpose, but a regular. And this is important, the input shape, 28 by 28 by 1. This is what we saw in our in the generator model. Our generator model outputs a shape of 28 by 28 by 1. Again, our activation, we've talked about dropout before. This is to help with overfitting. It sort of randomly drops the weights, and this helps with overfitting essentially. Another convolutional layer, same thing with everything else. And then we flatten the layer. We've talked about this. The discriminator is a classifier, it's a classification task. And so we want to flatten this because we want to feed this into a regular neural network, an artificial regular neural network, because it's a classification task. And so we flatten this 2D or 3D actually in this case, 2D image into a 1D image, just so we can feed it into our final layer, which is a dense of 1. I think we've talked about this, but it's 1 because it's a binary. We have two classes. Is it a 0 or is it a 1? And we only have 1 because we want some probability. And so it's only going to output some probability from 0. If it's 0.6, let's say the output is 0.6, then that corresponds to it being a prediction of being 1. And same with vice versa. And so we're only outputting one neuron. And this corresponds to the number of classes. For a binary classification test, we only have 1 class. Technically, too, it's a little confusing, but we only have 1 class in this case. Finally, the final thing is the loss, or how we code up the loss. Because it's a little different. We have 2 neural networks instead of the regular 1 neural network. So we have to have a little bit different loss. We create our discriminator and our generator using the functions we created in the previous slides. We assign cross entropy to be equal to the binary cross entropy. All right. Finally, our discriminator's loss. It's going to take in real output. Real output is our real images. It's also going to take in fake output. And so the real loss of our real images is going to be the cross entropy of our real output. Same with the fake loss. It's going to be the cross entropy of our fake output. Finally, the total loss, we add those together. Just like in the formula we had, the min-max operation, just like that. And finally, in the generator's loss, we only take in fake output because that's what the generator outputs, fake images. And so this is just going to be cross entropy of the fake output. So I know it was a little rushed, the code, but I think it gives a good idea of what's going on. And again, try to see this as a high level. The code, again, isn't too important. What's important is the min-max operation. It's a competition between the 2 different neural networks. One is a generator, one outputs images. You could output whatever you want, actually, but for our case, it's outputting an image. The other is a discriminator, it's a classifier. It's classifying, is it real, is it fake? And that's what's important. And hopefully this gives a good intuition of the generative adversarial network. And that's it. I'll stay for questions. But again, this is going to be our last lecture for this semester, essentially. And I want to do more projects. We didn't do too many projects this semester. But hopefully, if you have a good intuition of what's going on, we'll be able to do projects that have a sort of arbitrary solution, right? Where the solution can't be found from, say, a tutorial or say something else. And so you have to do a little bit more thinking, a little bit more learning. But I think these lectures have given a good intuition of what's going on. And hopefully you can use this in projects, and which we'll do next semester. So thank you everyone for coming. Hope you have a good holiday, and thank you.